Okay, cool. So let's see if I think this is working. Pretty sure it is. So hello and welcome to our sixth fall presentation on Missed Remote Learning. Many robotic students have lost the opportunity to obtain this hands-on experience that they used to have. Therefore, FTC Team 14 to 20, Nemesis Prime, has been reaching out to professionals, asking to give presentations about themselves, their professional journey, and about a fascinating topic about their specific profession.
Today, we have James Wilson, who has developed a variety of embedded software technologies for various types of devices, including tablets, computers, smartphones, security cameras, and networking devices. He's currently working as a software engineer at Qualcomm Technologies Incorporated, developing 5G low-level software. While at Qualcomm, he develops robotic softwares for Snapdragon flight board used for aerial and ground robots, which he'll be speaking more about throughout this presentation. In his free time, he enjoys flying drones with FPV goggles. Thank you for being here with us.
Thank you for having me. Thank you for the invite. So should I go ahead and just get started, or did you guys want to start with some questions first?
Yeah, you just get started with the presentation, and we'll ease on some questions as you go.
Okay, great. So as we mentioned in the introduction, I started out well, one of the projects I've worked on at Qualcomm is called the Snapdragon Flight, and it's so I got to throw in a little plug for Qualcomm in here. And this is a picture of the board over here, and so we always refer to it as the smartphone dividend, because smartphones are still our focus at Qualcomm, or a big part of what we do. But there's a lot of technology in smartphones that you can use for other things, and we're definitely interested in that. And one of the things we wanted to focus on, and still do, is robotics. So this is an example of a board that we created, and then a prototype platform. In fact, let me see. Do you guys know how to make a little mouse pointer appear? Let's see. Like annotate, or maybe this will work. Okay, so can you see? You can see that, right? Can you see that green line? Okay. Okay, so this is an example of a prototype that we created. So I've got my screen over here, so two different places. I apologize if I'm turning my head. But this prototype, basically, you can see at the bottom has three cameras. Actually, the big camera, that's where the point of the red arrow is. It's a 4K camera. At that time, that was fairly new. Now a lot of drones have 4K cameras. And then there's a camera on either side of it that actually provides stereo functionality. Actually, I don't think maybe this model doesn't have it, but we did have a board that does have a stereo camera. So that's a total of 3 cameras. And there was another downward facing camera that's used for optical tracking, so that we can track the motion of the drone over ground. Anyway, a lot of features. And what you'll see is, as we go forward, is that this became a prototype that other companies could use to develop their drones and get them a head start in doing that. And there's a lot of resources that are now available for drone development, and we'll cover some of those in the presentation. So the hardware capabilities that we just talked about, stereo cameras, IMU, and IMU is a big part of what I just mentioned, was the smartphone dividend. And that's the primary sensor in a smartphone is the inertial measurement unit, and that allows you to determine the orientation of the smartphone. Whenever you rotate the smartphone, how the screen reorients to account for the new position of the smartphone. That happens with an IMU sensor, and that sensor is a lot more accurate than you actually get a sense of just from normal use of a smartphone. So that's included in our board, and it's part of the thing that allows us to actually fly. And I'll get into that in more detail later. Some of these other sensors are less critical for operating a drone, but they help with the overall quality of the flight. So let me give you some idea of how we got started. We didn't start from, this board right here was not what we started with. We had to start with a prototype, and this happens a lot in engineering. And I'm sure if you guys build robots, you know how this goes. You have an idea for something, and you don't want to build the actual implementation until you're sure it's the right approach. So this board that we used was a much larger board with similar functionality. It was not intended to be on a drone, and you can see, how big it is. This is not what you'd want to be flying, and it's really fragile. And we had wires all over the place, but this was an appropriate way for us to get off the ground and verify that the processor we wanted to use, which was originally intended for a smartphone, would actually work in the context of a drone. So we took the next step from there. We used a smaller board, which you can't really see, but you don't see this much anymore. When people build drones nowadays, they generally just start flying and follow a few safety procedures, which we'll cover toward the end. But they assume that it's going to fly. We weren't able to make that assumption because we were doing most everything from scratch. So we surrounded the environment with a net for obvious reasons, because we had no idea where it was going to go. And if you look here, you can see we actually had it tethered as well. That's right here. And oh wow, I got all these accumulating green lines. How do I clear? Okay, clear all drawings. Okay, there we go. And so you can see this, this red line actually contained power and data as well. So there was a power cable, and we put the battery over here, and so we could fly for a longer period of time. And then somebody was actually supposed to hold this counterweight because we didn't really know if there'd be enough thrust generated by the propellers to achieve flight. So we were trying to effectively simulate zero gravity, with this tether, but it helped, but it introduces a lot of artifacts. Just the fact that we're hanging something essentially accomplishes, is just testing attitude control. It's not testing our ability to accurately generate enough thrust to get off the ground. And you need both. You need both attitude control, and you also need the ability to control lift as well. And we weren't testing that with this kind of setup. So let me clear that, or clear all the drawings. Go to the next slide. And so what we eventually achieved, these are some of our customers. It got a lot smaller, as you can see. So here's a drone here. This one, small. I'd say it's probably about the size of a big wallet. And then the arms fold in there, and then this one actually folds into about the size of a paperback book. And you can kind of see what our customer, which would have been, if you were a customer of theirs, you would have bought directly from them. They wanted it to be completely protected from the outside world, so if this wouldn't hurt anybody. And this drone, the use case for this is that you just take this with you, pull it out from a purse or a backpack, and you turn it on, open it up, and then let it hover, and then it actually acts as a camera for you to take family pictures, without having the benefit of a tripod. So here's another one here as well. You can see, remember we were talking about that front camera, and then things started to get bigger over time as the customers got more sophisticated, and industrial use cases came on the scene. So for us, our first exposure as a company in drones was more in the consumer world, because we have lots of consumer customers, through the smartphone channels. But then over time, we began to discover that drones actually are very applicable in an industrial setting as well. So, that's one of the drones here. And then this is, you may recognize this. This is this flies on board. Sorry, this flies, close the door. So this flies on the Mars, the latest Mars rover, which is in progress. It's about halfway to Mars now. It's due to land in February of this year. And you can see the image of this newest Mars rover after it will land. It's a computerized rendering. And it's very similar to the current Mars rover, Curiosity, that's on the surface of Mars now, but with a lot of additional instruments and more payload. So one of the experiments that this, I think the Mars, so it's not Curiosity, what's it called? Gosh, I can't remember the new name. Anyway, but it's carrying a helicopter, and at some point they will dispatch this helicopter from the inside, from the kind of the center section of, like inside here, the center section of the drone. It'll drop to the ground, center section of the robot. The drone will drop to the ground. It will unfold itself, and then the drone will take off and conduct some aerial photography on the surface of Mars. And it'll do that a few times, and then charging with the solar array that's at the very top. And this is using a Snapdragon processor, the same one that we were looking at before, for the photography. And I believe they have a secondary controller to do the flight control. And what you see is two rotors here. So we're going to be talking today about quadcopters. And this is a coaxial copter. You could call it a bicopter, but I think people generally refer to it as coaxial copter. And JPL, that engineered this along with the Mars rover, decided to go with the coaxial design. And I'm speculating a little bit here, but I think it's probably for stability, because it's you don't have to worry about four rotors. You only have two, and there's intrinsic aerodynamic stability with these two rotors spinning in opposition to one another. So it's mechanically a simpler design, fewer motors. You can do this with one motor. Then they have to have, they've got to have some control arms on either side to adjust the pitch of the rotors so they can achieve transverse motion as well as, the vertical motion. The vertical motion just occurs from from spinning the rotors at the same relative speed, but in opposite directions. Anyway, it's a good design, and it's not fast and maneuverable, and it's not going to fly upside down. And so it's not very common in the FPV drone world or in the consumer drone world, because you can't do a lot of acrobatics with it. But for their purposes, it's a good approach. So I definitely tune in on February to the JPL NASA coverage. If you haven't seen it before, it's very exciting. They give you a live view of the engineers that are waiting for a signal to come back from the Mars lander as soon as it detaches from something they call the sky crane. And those first few critical seconds allow them to determine if it survived the reentry and actually did land without damaging itself. But anyway, it's very exciting. Everybody, if you haven't seen it before, you should watch a past Curiosity landing on YouTube, and everyone screams and they're happy. Because this, for the people that work on these projects, it's quite different from working at Qualcomm. This is the culmination of probably well over a decade worth of work. So all of their whole 10 years worth of work comes down into these last few moments. So I was excited to think that my little contribution to consumer drones ended up on Mars. So, and that's happens, as in the engineering world. It's part of the engineering profession, which is always great.
So I have a question.
Sure, go ahead.
So what's the camera quality like on these drones?
Well, that's evolved a lot. So right now, that particular drone had a 4K front-facing camera, so it was capable of doing 4K streaming videos stored to an onboard SD card, and also could do stills at slightly higher resolution. So it's hard to assess how to assess the quality. But now, today's drones like the DJI, DJI is probably the leader in consumer drones, and they have one called the Mavic Pro. And the Mavic Pro flies 4K cameras with a 1-inch image sensor that's capable of high dynamic range and very controlled light exposure using uncompressed video. And the quality of the images are amazing. And it's gimbal stabilized, so that means that the camera doesn't move with the vibrations of the quadcopter. So you get really smooth video. So I hope that answers your question. I can't really tell you too much more about it because I'm not a camera buff, other than just the resolution and the size of the sensor. So So I'm going to intermix, as we talk about drones, I will intermix questions about what it takes to be, why, about engineering and what are some of the major things you need to learn as you go to college to become an engineer, and the path to getting to be, to becoming an engineer. What are some of the big things that you need to hold on to? It's not as complicated as you think. So anyway, let me start with this question. Why do people go to college to become engineers? As an alternative, why not just start working as an engineer right away? 'Cause some people do that, but why do some people choose to go to college? Any ideas, Gavin or Darren?
I would guess just to like kind of get a hands-on experience and try to learn more. Would that be it?
Yeah, no, that's definitely a valid reason, and I would agree with that. That's definitely a valid reason. It's not the one I'm going to try and impress you guys with, but that's definitely a good reason. So let me say this is probably not the one you guys are going to answer. Some people go because everyone else is going. So that's an okay reason, but it's not going to keep you as interested as if you have your own personal reason. So to master the latest and greatest technology, Gavin, that's kind of what you were leading to, and that's definitely a common reason. To make connections with campus recruiters, so that's another way of saying, well, you can get a great job, which you can get an internship. When you're at school, you reach a certain level. At some point, the campus recruiters will come by. If you can get an internship, definitely do it, because it's a great way of getting exposure to the company to see what you like doing. And then it also lets them see what you're capable of. And oftentimes it leads to getting hired. We do internships at Qualcomm a lot. And we many, many times hire the interns, or we give them a job offer, and 6 to 7 months later after they graduate, they decide if they want to take it. So it's a great setup. Sometimes you go to college to get into a good graduate school. I've seen people do this so that they love research. They want to stay in school and get their doctoral degree, and then the undergraduate degree serves as a stepping stone for that and to carry on their work and research. So it's also some great reasons. So we're going to come back to that. Let's get back to drones. So how does a drone fly? Specifically, when I say drone, I'm going to say a drone in the context of a quadcopter. So how does a quadcopter fly? And it's in the way quadcopters fly is with 4 propellers, as the name implies. And there are 2 of the propellers will spin in one direction. And you can see here, the red is spinning counterclockwise, and the other 2 are spinning clockwise. Now we could reverse it. This one could be counterclockwise, and this one could be counterclockwise, but they always have to be opposite one another, and the pairs have to be spinning in opposite directions. And any idea why that is? Let's say we had all the propellers spinning in the same direction. Let's say everything was spinning clockwise. Any ideas what would happen if you had a drone like that?
I'm guessing things will be probably will lean one way, won't be balanced.
Yeah, that's correct. What'll start to happen, that imbalance you're talking about will start at spinning, and it will spin in the direction of rotation of the rotors. So if we had taken all 4 of these guys and spun them clockwise, all 4 rotors, the drone itself would begin spinning clockwise as well. So it would get off the ground. You would accomplish that, but you'd never be able to stop. The drone would start spinning as it got off the ground, and it would start spinning faster and faster and faster. Eventually, you'd lose control of the drone. Most people don't want to just spin around in circles when they fly. So, and there's a mechanical property of the rotation of these propellers that imparts angular momentum to the body frame of the drone. So we need to counteract the angular momentum imparted by the clockwise motion of the propellers with counterclockwise motion of these propellers. And then we get stable lift, meaning the quadcopter will just rise from the ground, and not rotate until you tell it to. So, and then if you want, so that gives us lift. And whenever you're trying to fly, you need not only lift, you need control of your attitude. and attitude with anything that flies, be it planes or whatever goes in the air. You have attitude is controlled with yaw, pitch, and roll. So in this case, we've got we're going to call this one, at a quadcopter, since a quadcopter is symmetrical, yaw and pitch, yaw and roll. You have to pick a forward direction before we know what roll and pitch is. So let's assume, and yaw, let's assume that this is our forward direction. So if this was our forward direction, then to achieve roll, we would be rolling on this axis here. And if we were going to yaw, if we were going to change pitch, then we'd be rolling on this axis here, and my drawing makes it a little bit hard to see. So if we need to control pitch, it's kind of intuitive. Let me grab a quadcopter from back here. If we wanted to control pitch on this quadcopter, and I would add additional thrust to the rear pair of motors and less thrust to the forward pair, and that would cause the quadcopter to tilt forward. It kind of makes sense, because if you have more thrust in the back and less thrust in the front, it's going to pull forward. And that's good, because if you want to fly forward, you need to increase your pitch. If you want to fly backward, just the opposite, more thrust here, less thrust in the back, we're going to pitch back. So if you're writing software for this drone, controlling pitch, not too hard. Same with roll. You're going to add additional thrust on the left side if you want to roll right, additional thrust on the right side if you want to roll left. So got that down. The harder one is this yaw. Remember how I was saying that if we made all the motors turn in the same direction, that we would begin to rotate in the direction that the motors are rotating in. So what you can do, though, is change the angular velocity of motor pairs to allow the quadcopter to slowly rotate in the direction of the dominant pair of motors. So in other words, if these motors were spinning clockwise and I slow them down as a pair, then I would start to move counterclockwise and back in the other way as well. So that gives us yaw control. And that principle is applied all the time. That is the basic principle of maneuverability for yaw, pitch, and roll in a quadcopter. And everything else is a variation on that theme. And we'll see as we go on, people have been very creative about how to place these. Some quadcopters will fly in a plus configuration, where there's one motor in the front, one motor in the back and on the sides. This one is an X configuration, and that front is designated as the direction of forward motion between the two motors that are on either side. This configuration is a lot more common. The X configuration is more common. The plus configuration that I mentioned before, where let's say the camera was pointing this way, this plus configuration is very uncommon. And the main reason that is that the propeller would get in the camera's field of view. And you were talking about camera quality. Well, we don't want a propeller in the field of view, and especially if you're trying to fly through the camera, which this quadcopter is designed to do. I need to be able to see where the drone's going without being obstructed. So anyway, okay, so next, that covers how we fly. So the next thing, so we covered how to fly. The next thing is propellers provide the lift. And I'll start skipping around a little bit because we're going to run out of time. I'll try to keep it down to an hour if that's okay. Is that everybody can last an hour? Okay, good. So the thing to know about the propeller is that there are usually two measures that you want to look at when you're choosing a propeller for your particular drone. And let me clear. And the common measure is pitch and diameter. And the diameter is kind of intuitively obvious. The bigger the diameter, the wider the prop is, the larger the circle it produces. So, and that's what you can see with these red circles below. The pitch is a little less obvious. So if you look at the propellers on this, the pitch is actually the twist in the individual blade of the propeller. And the more twist there is, the higher the pitch value. The higher the pitch value, the more the propeller will bite into the air and the more thrust it will generate. So the question would be, why not just create propellers with a vertical, very really high pitch, where there are right angles to the plane of the motor. That would be possible and that would work, but you really have to. That would be very hard for the motor to actually turn the propeller because there'd be so much air resistance coming from the propeller that we'd eventually overheat the motor. We wouldn't be able to sustain in other words, short answer is we get terrible battery life. So there's a balancing act between pitch, too much pitch, and we get terrible battery life, not enough pitch, we don't get enough thrust. So it's another variable. So as we go, what you're going to learn is when you design a quadcopter and you're picking the parts, you have a lot of different variables to account for, and each one has an overall effect on the capabilities of the drone. So we'll get into that as we go. So let's get back to our question. So my assertion for you guys today is, why do you go to college to become an engineer? And I will say to you, in my experience, the main thing they say that you can learn from college is how to learn. And what I'm trying to say here is that the information that you gain in college is, if it's of a technological nature, may or may not be applicable to what you would do later when you would go and go to a startup or go to a company, or because companies, colleges have a hard time keeping up, with the state of the art and technology. So it's questionable, whether or not that would be directly relevant. But one thing colleges are really good at is teaching you how to learn. And we're going to get into, and I'll give you some specific examples of that. But so just remember, the biggest takeaway from going to college is to become a learner, an independent learner, to learn how to learn. And we'll talk more about that as we go. Okay, so what does it mean to learn how to learn? I want to define that a little bit, and it's not just a Google search. Honestly, I use Google so much now. If I have a question about how to particular line of code, or the proper name for a function, or what this function does, that's a lot of things that software engineers typically do. Google is my friend. I would be much less productive without it. But if I have a question about how to approach a problem, or if I don't understand, how quadcopters fly, I can do a Google search. But if I'm going to read up on the mathematics of lift and prop pitch, I got to study. And how do I approach this problem and what to start studying? That comes from the practice you gain from completing coursework in college. So I say it's not about taking tests, but you got to take the tests. So just take them, get a good grade if you can, get them out of the way. I always stressed out taking tests in school, and I wish if I could do it over again, I would be more about, get it done, get as much as I can out of the test. But I didn't. I always had to get an A, and I was devastated when I didn't. Don't let yourself fall into that trap. It's more important sometimes to finish the course and move on than it is to be perfect. That expression now, I think that I had to learn the hard way, is perfection can be the enemy of the good. Meaning that just because you can't do it perfectly doesn't mean that it's still not a good experience. So, and I had to learn that. That was a hard lesson for me. So, so let's go back to drones. So when you look at a drone, this pattern is repeated in every single quadcopter that you will find. They all have speed controllers. So the speed controller is here, and they're called ESCs. ESC stands for electronic speed controller, and there'll be one for each motor. Now you may not see it because it'll be combined into a small board, but they're there because they all have to, each motor needs its own independent microcontroller to control the speed of the motor. This is where the software is running, by the way, that's controlling how the pulses that go over these three electrical connections that cause the coils in the motor to energize. There's a small processor in here that's doing the work of figuring out just exactly how to ramp the speed of that motor as it's rotating, because you can't just tell the motor to instantly start rotating. You have to gradually control the motor, and the rate at which you pulse each of these coils changes as a function of the rotational velocity of the motor. So good bit of math in here. And that's where you need a separate microcontroller for each of these. There's the battery. That kind of goes without saying. Although a lot of technology in here, that's changing over time. And this power distribution board is where the control of the current that comes from the battery, the control of that current occurs here in this power distribution board. And there's there's different types of components. They're usually called FETs, and their objective is to control the amount of current and the voltage, and to sustain that voltage at a certain level. So we keep the ESCs happy, because the ESCs are going to feed power to these motors. So not as complicated, but still important. And then there's the flight controller. And the flight controller is the primary processor on the board. And that was the thing that Snapdragon contributed to at Qualcomm. We were using a Qualcomm processor on the flight controller for those prototypes that I showed you at the beginning of the presentation. And that's where kind of the heart of the drone is. And it's taking sensor data. From the sensor data, it's calculating the current orientation of the drone. It's getting input from the remote control of the person who's steering the drone. And it's deciding, okay, there's a calculation involved associated with this, and we'll get into it a little bit. I know the software has to say to itself, the algorithm is saying, I know what my current orientation is. I know the commanded orientation. So what do I need to do to change the relative velocity of the motors to achieve that commanded rotation? And sounds simple, right? You're flying along like this. Somebody with their joysticks rolls to the right. So you get that input in your flight controller, and then you decide to add a little bit more thrust over to the left side, and you're done. The software itself is done. And the software is going in this loop over and over again, looking at the sensors, looking at the input from the person with the remote controller, actuating motors, sensors, remote controller, motors, sensors, remote controller, motors, very, very, very fast. The faster it can do that processing loop, the more stable and smooth is the motion of the drone. And we'll see a little bit more of that in detail.
So when it comes to the placement of the motors, do they have to be equidistant to the center and like 90 degrees straight on, or is there a little bit more margin for error?
That's a good question. They don't have to be equidistant. It's common. In fact, I'd say it's mathematically it's more balanced. It's easier to calculate thrust if you know the contribution to the overall lift of the airframe is the same. Because what happens is let's say, so this is common. There's a thing called a dead cat configuration. I hate this reference, by the way, because I'm a cat person. But the dead cat drone configuration is two arms going straight out, to your point, to the straight out here, and that's to get it out of the way of the camera so we can get good, clear video, particularly for photography purposes. And then the arms in the back will usually be a little bit longer sometimes. I'm not sure. Sometimes the length varies. I don't recall, but it'll be at a totally different orientation. So what happens is, because the lengths of the arms are different, the thrust that's applied to the motor will produce a different amount of thrust, a different amount of lift to the overall airframe, because the length of the moment arm is different for the front arms than it is for the back. And so now you've got to calculate that. And so usually people will go with this balance configuration, but there's a lot of good reasons for not doing that. But then you need to account for that in your flight controller, that you're getting different thrust from each arm now. And even though you might be spinning the motors at the same velocity, the motors will produce different thrust in the back where the arms are a different length than the arms in the front. So it's just harder to do. You got to account for that. So one of the big variables that we talked about is making sure you've got the right propellers. And I won't go into too many details on that, other than to say the bigger the propeller, the more thrust you get. However, the bigger the propeller, the more power and more battery power it requires to turn that propeller. You know this expression, there is no free lunch. So, you could say, well, okay, if I need more thrust, I'm just going to use a bigger propeller. And then if you use the same battery, your battery life is not going to be good. So if your objective is to achieve a certain minimum flight time, and you knew that you had to carry a higher payload, you might just say, I'll put bigger propellers on there. But then you might not be able to sustain that minimum flight time requirement you have. So you're building your drone. This is the basic design. You've got to select the props. You've got to select the right motor. So I think I won't go over this in too much detail, but the bigger the motor, the bigger the prop. But there's a key component of the motor you have to remember is that these motors are rated in terms of kV. So as a general rule, 2 motors of the same size, and usually the size is a function of the diameter of the motor and the height of the motor, those 2 numbers. 2 motors of the same size, one with a low kV and the other with a high kV. The lower kV motor will spin a larger prop. And that's because it's able to generate more torque. So it'll handle the larger prop. So if you need a larger prop, like we were just talking about, and you knew that you knew what size motor you were going to get, you would get the one with the lower kV rating. It gets a little more complicated than that, but I have a tool I'll show you later that simplifies things. So let's talk about the ESC. So if you're going to become a software engineer, there's a lot of software content in the flight controller, which is in the middle here. A little hard to see, but the flight controller is in the center. So, and this one, the ESCs are also in the center. Sometimes the ESCs will be on the arm, but the ESCs have their own software as well. So typically they have a 32-bit microcontroller, the newer ones do, and they're capable of dynamic control, which is a really nice feature. That's something that hasn't been around for all that long. What that means is that the ESC is going to decide to actuate the motor in a certain way, pulse the motor to generate rotation, but it doesn't really know if the motor is going to spin that fast or not. It just knows that algorithmically speaking, it should spin that fast. In the old days, that's all you had. And then you needed to use the IMU to determine if you were actually achieved the orientation that you wanted. That was your point of feedback. But now not only do you have the IMU for your feedback, which is what the flight controller is using, but now you've got the motor itself. With these newer ESCs, the motor will tell you how fast it's spinning. So that gives the software, that loop that's running real fast on these ESCs, a chance to actually adjust with feedback. In fact, you guys have built robots, you're familiar with a PID loop? Did that ever come up if you're trying to control the rate of rotation of your motors to account for resistance in your drivetrain? The PID loops, did you ever use a PID loop?
Yeah, students have worked with PID loops.
Okay, so these use PID loops too. Same PID loop. The ESCs that are used for motor control have a PID loop. The flight controller also has a PID loop. Now, over time, people have really have enhanced the PID loops to add a lot more coefficients and more fine tuning capability, more constants that you can adjust, and gets really complicated, but it's a lot of fun. If you like tuning things, you can do all kinds of tuning now. So lots of PID loops, and we're going to cover that as well. So we talked about the battery. So you guys will have a copy of the slides, and you can come back and look at this later. But it's sufficient to know that batteries are limited in the amount of current that they can source. So if I knew that each of the ESCs were expected to consume 30 amps, and I have 4 of them, I would need a battery that could source 120 amps. So you can look at the rating on the battery, and the C rating of the battery will give you some idea of how much current it can source. So now that you've got all these different variables, you're picking your motors, you're picking your airframe, picking propellers, and now you're picking batteries. And it's a little hard. It can be mind-boggling because really what you want is most people want a drone and they want to define it in the context of maximum thrust, maximum flight time, and payload capacity. And there's probably some others that, it's more mission-oriented parameters. So there's this tool that's available online at this URL here at the bottom, and that tool will allow you to input your desired mission parameters and then tell you what all the other variables that we just talked about would be. You know, size of the prop, size of the battery, size of the motors, that kind of thing. And then you can play around with these variables and say, okay, well, I can't make the battery that big. That would increase my payload too much or take away from my maximum payload. So if I was to do a smaller battery, you know, maybe I could do that with smaller motors, you know, then you can just play with the variables. So here's some best practices for quadcopter design. So these are just some things you can do that people have had to spend years of effort learning. So pays to, you know, learn from their mistakes. So very simple thing, you know, this just stick some rubber grommets underneath the flight controller, because this flight controller has an IMU on it. The IMU contains, it's a chip that contains an accelerometer and a gyro. The accelerometer lets the chip determine G-force in a transverse direction, and the gyro lets the chip determine G-force rotationally. And you combine those to determine the orientation of the quadcopter. So anyway, that gyro is here on this guy, and you want to cushion it as much as you can because vibrations create noise, and that means that the software has to do more filtering on that IMU data to determine the orientation, actual orientation of the drone. So the smoother it is, the better. You want to you want to also do vibration dampening on the motors as well, because the motors are another source of vibration. And if you can actually dampen the IMU itself, this one actually is interesting. I think this has kind of fallen out of favor in the hobbyist drone community. But the IMU itself is mounted on this ribbon cable, on this little flex cable, I should say. And the flex cable kind of acts as a shock absorber for the IMU. And I don't think that's being done so much anymore because this is a point of failure if you have a crash. And you can see this flex cable just getting ripped off. And there's some epic crashes if you're flying along at 100 miles an hour. And it's not uncommon for drones to fly at that speed, you know, if it's built for racing. And if you hit something at 100 miles an hour, it's amazing how every little thing that you think could break, you know, it just breaks. It's terrible. And you got to go and fix it. But that's kind of part of the learning process. So what else? It helps to, you know, minimize the aerodynamic drag. Yeah, that helps. That's not such a big deal now. I think it still is, but you can make anything fly nowadays because the flight controllers, the software, the motors, and the batteries are so good. But if you can make things move through the air a little bit more smoothly, then you're wasting less power. What else do we? This one is a big one: design an airframe that's serviceable. So if you look at this one, you can kind of see I've got some screws right here. So if the arm breaks, I can replace the arm just by unscrewing it. So when you look at an airframe and you're not trying to make a decision, don't just, you know, buy the one that looks cool. try to imagine what's going to happen to the airframe when it dives into the ground at 100 miles an hour, and you know what might happen to it. And that's not something you can just look at and know. You'll just gain some knowledge. You'll know, okay, the last time I bought an airframe, this thing, see how this camera's sticking out? If I hit a tree, chances are that camera is going to take it. You know, if I was unlucky enough and a branch just gets in between. So these are, you know, kind of over time, you know, you learn where your vulnerable areas are. So any questions up to this point?
So I just have one general question. So how did you get into making these drones? This is a more general question.
Oh, yeah. That's a good question, actually, because I was very lucky in that Qualcomm decided to start building flight controllers with its chipset that's normally used in smartphones. And I had no exposure really to drones at that point. I knew robotics like you guys do, but ground robots primarily. I'd spent a lot of time building ground robots, mostly for personal objectives, you know, not because I was doing it at Qualcomm. So I had learned how to learn through my education in college, and I knew what information I needed to gain, and I started studying. And today it's a lot easier to get up to speed on quadcopters because the resources that are available online are so good. We're having this talk today, for example. At the very end of the presentation, I'll give you a list of open source projects that give you all the software you would need, including the motor controllers. So that's what I would have studied. I studied some open source. I didn't have as much to choose from, but I studied open source to see how they would make it fly. I tried using that open source to make one of our, to make a prototype fly. I learned a lot from that process. And I made a lot of mistakes. You have to be willing to make some mistakes along the way, just so that you can gain the experience that comes from it.
Also, have you personally been able to like go through the drone, like maybe make a project out of it, like a video?
Yeah. So I for a while I thought I was going to do. So this is one of the drones I built a while back. This is a really ugly drone. Don't build a drone like this, guys. But this is the drone I built to do video projects. And let me show you the front. Nowadays, the materials that are available are much nicer looking than this, more self-contained. This has got wires all over the place. So see the gimbal here at the bottom there? And so it doesn't have a camera in it now, but it would carry the camera. And this was a gimbal that would perform stabilization of the camera orientation in X and Y. And yaw, pitch, and roll. So so the camera actually had its own little yaw, pitch, and roll controller to compensate for vibrations from the airframe. So no matter what, if I had this powered up and I had a camera in there, no matter what the orientation of the airframe, the camera would stabilize. So I did a little some video capture with this, and it's got a GPS antenna on the front, very big motor, big propellers. But I lost interest in video, to be honest. What kept my interest was speed. I'm not a guy that jumps out of planes or anything. So I don't think of myself as an adrenaline junkie, and I don't drive fast cars. But oh, what a thrill it is, to fly along. I am. So here's a pair of, this is digital goggles now. So we don't use some people still use analog video, but this is the latest from DJI, and it provides high quality, high def video of the video coming from the drone. And I feel like I'm in the air. I feel like a bird, even though I'm totally focused. I'm standing on the ground and I'm focused on where the drone is going, watching that video. I still feel like I'm there, and this never got old. But video editing and aerial photography got old for me. So here I am. This is what I look like when I fly with my, usually my head goes down. This is very common when you see people doing FPV drone racing, their heads always go down. Well, there's got to be some research that needs to be done to figure out why. And then you've got your remote controller there. So anyway, great experience. You don't have to buy these particular goggles, but I recommend if you ever do build a drone that you put a camera on it that gives you the ability to look at the video while flying, with goggles. Ton of fun. Got to put the glasses back on. Some of the goggles will let you fly with glasses, those don't. So we're back to building a drone. I'm going to go through these two real fast. We talked about an IMU. Got to pick a good IMU. And we were talking about the PID loop. I won't go into the details of the PID loop, but if you guys have some exposure, this is the basic principle behind the PID loop. You have input coming from the sensors, and you have estimation of your attitude in the center, and then these coefficients, the PI and D coefficients, to tune how the attitude is estimated from the input, from the sensor input. And actually, I'm probably saying this incorrectly. I think actually the PID coefficients are used to tune the output from the PID loop. Anyway, the output in this case is motor control. So we have sensor input, motor control in the output, and then feedback coming from the sensors. So, and then we have control input as well, from the pilot. So this PID loops are probably the most popular control algorithm on the planet, and they're still used everywhere in drones and in many things. Very popular, and a lot of work has been done on refining these PID loops for drones. So let's get back to our topic. We were talking about our engineering topic of learning how to learn. So how do you learn how to learn? I think the essence of learning how to learn is learning how to ask questions. And you guys were asking some good questions. I can remember times in my classes in college where I was always embarrassed to ask questions, and because I didn't want to look stupid. So sometimes I would ask a question that I knew the professor already had the answer for. So I could look better. That's kind of a waste of time, but I would still do that. I'm embarrassed about that. But then thankfully, there was almost always at least one person in the class who would ask the question I had, and I would dub them in my brain, as the spokesman for class ignorance. And I would love it if there, we had at least one person in the class that would be our spokesman. But don't be that, don't be embarrassed to ask questions. Always that, and people that teach classes, as I'm sure teachers will tell you, they want you to ask questions because that's how they know you care about the subject matter. So ask lots of questions. Be persistent, even in the face of failure. So that means failure taking your test. Don't give up. Stay with the class. Don't leave the class. If you're doing an experiment on your own, and you're building a drone, let's say, like where we. So this big ugly drone. There was one that came before it. I launched. It turned upside down. To this day, I cannot tell you why it turned upside down. And while it was inverted, it continued, the motors just continued to stay powered, and it just flew right down into the ground and into a million pieces. So I've never forgotten that. I don't think I have any video of it, but I came back and got better the next time. So don't give up. There's nothing more satisfying than solving the mystery. So in the context of building a drone, that would be making it fly. And if you spend a lot of time going through the effort to construct this thing, and you build it from scratch, and you actually see it work, and you're controlling it, and that's an amazing experience. And that is, I think, the most gratifying part about all forms of engineering: the impulse to build and satisfaction in seeing your imagination take form and become real. So, and the other is, learning how to study when no one's giving you a grade. That if you take nothing away from college, at least take away the study skills you need to gain the knowledge in the area that you need to study for, to achieve the skill you need to accomplish the task, and learn how to do it even if nobody's telling you that you have to do it. And that might come in the form of, some you go to work, or you have a startup and you have an idea for what that startup is going to do and the product it'll build. How do you find out how to do that? You might have the idea, but you might not know how to get there. So now the grade is whether or not you can actually build that thing and make it work. And that's the thing that will motivate you then. So in order to get to this stage, where you've learned how to learn, I think for me anyway, the thing that was most important to me was learning. I always thought about it as learning how to read again, because if you're needing to teach yourself a new topic, invariably you're going to encounter research papers that represent the state of the art, well before it's actually implemented by anybody else. In order to read those research papers, you're going to need math. And math gives you the fundamental underpinnings to understand that research, because ultimately the answer will be expressed mathematically at some point in that paper. It might have tons of narrative, lots of verbiage. You get to the end, there'll be some equations there. This happens to us even at Qualcomm. I'll have a research paper that I need to read to understand what the approach somebody else is taking. Or if I'm lucky enough, I get to write my own research paper. And at some point, I'll have to express the essence of the problem mathematically. In order to do that, I have to be able to communicate math. Physics is important too. And for a drone, that's particularly important. Not always important in the software world, but helps to have an underpinning of the basic principles of mechanics and motion. And that applies certainly to drones and even, I think, even just to the real world, because it gives you a sense of how difficult something is going to be, just to have a basic underpinning in physics. True for chemistry as well. So we were talking about battery technology, and there's a lot of advanced chemistry that's going into the creation of new battery designs, and that is a whole new field in and of itself where you can specialize as a chemist. So to me, I think of these kind of as the three key areas of college coursework that it helps to finish. You don't have to get an A, but finish it because it gives you the ability to read and write in the scientific community. And then once you can read and write in that community, now you can start to learn, and you become, you will have learned how to learn, and you'll become independent of the classroom. So I'm going to skip this. This is just another diagram on a particular open source flight stack called PX4. The URL for PX4 is here at the bottom. And it's been around a long time. I highly recommend it. And there's actually some Qualcomm source code up there as well, I think, although I don't, may or may not still be there, but great open source flight stack. So this is, if you want to understand how attitude estimation works mathematically, this is the path name to find that source code for an EKF, an extended Kalman filter. A very popular algorithm for attitude estimation. The position controller part of it, that's where the source code is for that. The attitude and the rate controller. So what they tried to do with the PX4 flight stack, and every flight stack is different, they tried to divide the processing of the sensor data coming into the flight controller and then the ultimate motor actuation into these separate modules. So PX4, as I mentioned, is one of the options we talked about here. There's another very popular flight stack. It's probably the one I use most commonly when I buy a flight controller, for example, and I just want to, stick it on my drone. I don't want to have to look at any software or anything. I make sure that it has Betaflight on it, because Betaflight is frequently updated. It's available in source form, and there are various utilities like the configurator that allow me to actually change some of these coefficients we talked about for tuning the attitude and configuring it for my specific drone. So really good flight stack. Another one is ArduPilot. And ArduPilot has been around probably longer than any of them, including Betaflight. Very mature software, very well documented, runs on a variety of processors. So I highly recommend it. In fact, that's probably my #1 recommendation. If you want to understand how drones work at the software level, I'd start with this. And it is useful in ground robots as well. There's actually an implementation of the same software that a derivative of it that will work for ground robots. Because ground robots are essentially drones just flying in X and Y. Don't have to worry about Z. So there's a lot of overlap in the two. What's interesting is that there are many forks of Betaflight. Are you guys familiar with that term, forking? Okay, so what if you use an open source repo to develop a project, and then usually the better way of doing that, and this is how we would approach it at Qualcomm, is to add to that source code. If I needed a new capability, I'm going to go ahead and take the time to write it, but I'm not going to do it in a way that would break the other stuff that's already there. And then I'll add it back into the repo to add to the overall capabilities of that source code. So that's one way of doing things. And there's terms in GitHub like pull request, merge request. These are all part of the process, the workflow you go through to add back to the open source repo. Okay, let's say now you're going to create a startup company and it's just going to be too much work and you need a rapid prototype and you don't want to have to do it in a way that, keeps all that other stuff working. You want to just hack it up a bit, or you want to start from scratch, but you want to use the existing code as a foundation to begin. The term for that is forking. And basically it just means that you're going to make a copy of the repo into your own workspace in GitHub. And GitHub uses that term, when you have your GitHub account and you find a repo you like, if you log in to GitHub and then you find that repo you like, there'll be a little icon up there that says, do you want to fork this repo? And what GitHub is doing is literally taking a copy of that source code and making a private copy just in your workspace so that you can make changes. And then none of your changes will interfere with the upstream. It's another term. The upstream is, the common one that everybody's working on. So forking, there've been a lot of forks of Betaflight, too many to list. I can't tell you how many. And so what people have said is, I like Betaflight, but it doesn't do navigation really well. I like Betaflight, but I can't do waypoints. I like Betaflight, but it doesn't support all these different sensors I want. So that every time they said that, it became a new fork. And there's some really good forks out there. It's amazing how hard people work to create these forks and then make it available back into the community. So any questions so far? Okay, I'll keep going. Go ahead.
So one thing I have a question on. So we all know so they have like certain software to fly the certain drones and stuff. So do you know the language of code that would be used for this?
Yeah, that's a good question. So most of this is done in C. So it's a good question for you. So if you wanted to, a broader question behind that is, if you were going to learn a language, that you would help make you more marketable and be of service to you after you leave college, you're going to become an independent learner, and you're going to want to use a language maybe that's going to help you achieve some particular function. C is one of the ones I put on the list, C and Python. And I think I'd learned at least those two languages. And then there are various other special purpose languages, JavaScript with Node.js, for creating user interfaces. Each language tends to have its strength. So C was used for flight stacks because it works really well with low-end processors, they're not processors that are going to run Linux, but they're processors that are going to do something very simple algorithmically, but very fast, like the ESC or the flight controller. So C is great on those. So learn C, get good at understanding C. And the quickest way of learning C is go to those flight stacks I told you about. Go to Betaflight, go to ArduPilot, and look at the C code there. In fact, I was just going to say, get an Ardu processor, one of these boards. I can't remember. ArduPilot actually uses that prefix Ardu, but it's not limited to the Ardu processors. But you can write in C code in an embedded environment, just with one of those little what are those controllers called that you can buy from Adafruit? Anyway, but yeah, C is very easy. What's Ardu? What is the name of that development environment that begins with Ardu something? You guys remember it? You haven't used it? Okay, never mind. So anyway, learn C is a short answer. So I say, if you're going to become an independent learner, if you're going to learn how to learn, so I apologize up front to the mathematicians among us. I say it's okay to hate math because the reason I say that is because I don't want you to feel awkward about not being good at math, because you can still be an average mathematician and still be a great engineer. And you could still never really gel, with math. You study math, you finish the coursework, but it isn't your passion. That's okay. You can still be a good engineer and you can still be a good scientist, but you do have to finish it because it's so essential for understanding all those research papers and some of those things we talked about before about how to control the attitude of the quadcopter using those PID loops. That's going to be expressed mathematically with sigma notation You're going to want to look at those equations and understand them. So finish the math and practice, practice, practice. I'd say that's the only thing that made me halfway decent math is always do the homework assignments that they tell you, because they make such a difference. There are other classes where memorization will get you by, but not mathematics. You have to practice. So I'm sure Matthew will testify to that. There's no hiding. You can't cram your way into math. So anyway, and I would say if you we'll get to this point, where when you demonstrate, when you've learned how to learn, there's almost nothing you can't do, and nothing you can't build. And I would say, this is obviously not real, but if you wanted to build yourself a flying car, how might you approach the problem if you were an independent learner and you just graduated from college? So let's say from what we know today, let me ask you guys, would this car fly and why not? Just the simple answer. The props, are those big enough to carry all this weight? Probably not, no. So that'd be a lot bigger, right? So we learned that today from this presentation. We only have 2 props, which makes this a bicopter, is a common term for that. Is that enough? You can actually fly on 2 props. So what would you have to do? Any idea? Let's say these props were large enough, let's say the motors were strong enough, what would you have to do to these props to achieve stability while in flight, to keep it level, keep the car level? Any ideas?
So would you have the 2 propellers, one going counterclockwise, one going clockwise in this case?
You would, yeah. That would help you with your yaw, controlling the yaw. But what else? Let's say you wanted to control pitch. The car's going to want to tilt forward or backward. How would you control that with just these 2 motors?
The thrust back and forth, the front and back.
Well, that would be that would help, but you only have the motors on the side. And if you vary the thrust with the motors on the side, then you're going to get roll. You still won't get pitch. So let me give you the answer on this one. And what this approach still works. 2 motors will still work for you, but there's no, the expression again, there's no free lunch. You got to add another motor here so that you can tilt the rotor. So the tilting of the rotor will allow you to change the direction of thrust of the propeller itself, which will give you that pitch control that you need. So in other words, if we were pitched too far forward, you would tilt the motors back. The motors tilting back would cause the airframe to tilt back as well. So you'd have these motors on a very fast gimbal, and they would be moving back and forth very, very quickly to achieve the pitch balance that you need in the airframe. They'd be moving back and forth so quickly you probably wouldn't even be able to see it. So this car has other issues too. But it's a start, and of course we've got the wings. Any idea if the wings would be any help? What do you think? Because we didn't have none of our quadcopters had wings. Do you think the wings would help? Who says yes? Gavin, yes or no? Would the wings help?
I don't really think so. If it's going side to side, it might cause air resistance.
Okay. Yeah, so that's a good point. So if you were hovering and you wanted to move side to side, this would make it like a big kite. Good gust of wind would come along and push you in one direction or another. What about fast forward flight? Think the wings might help there? Assuming they were properly shaped. We're not going to generate any lift with these wings, but as it turns out, you can move fast forward and you would get some lift from the wings, just like you do from the wings on a plane. And that could help because now you don't need to generate as much upward thrust to sustain flight. And then more of your energy can be directed to a vertical or a horizontal thrust vector to get forward motion going, and then the wings will generate the lift for you. So there are some designs. So imagine, so you can see the elements here: wings, bicopter, and turns out that somebody actually did this. So you might recognize this. This is an Osprey. It's popular in San Diego, the Mira Mesa Air Force Base, not too far from Qualcomm, where Qualcomm is headquartered. Mira Mesa Marine Base, excuse me. These Ospreys fly out of, are located there. This particular one, I think, is a Japanese model, but they fly out of there and they carry lots of troops. But you can see the similarities. We've got, let me clear this here. We got a wing here. We got a wing here. Just like Chitty. We've got prop here and a prop here. So it's a bicopter. And then we were talking about changing the pitch of the propellers. It turns out, that we could do that here, and that it would work. But boy, look how hard this must have been. I'm trying to imagine the mechanical engineering that would have gone into the linkage to the motors, and then allowing because the motor has to exist in this whole assembly here, and somebody had to design the mechanical structure that would allow it to rotate fast, if necessary, to achieve the attitude correction that was required. So I would argue that somebody stole the idea from 1968 and built it in 1997. So I'm sure they didn't see it at that time, as the case, but the concepts are the same. So somebody learned. They probably didn't learn from Chitty, but they obviously did learn, and this is one of the things that came out of it. So let's get back to, we're almost done. Let me just give you close with saying, if you're going to build a quadcopter, be safe. I really did almost poke my eye out. I was building that large quadcopter I was pointing to. I was testing the predecessor to that one, and I was not wearing eye protection. And you guys that are in FTC are used to wearing eye protection. That is really good. I did not do that. So what happened was I was testing full throttle, and I was by myself in a room. At least I had the good sense of doing that, because I thought if it got out of control, I didn't want it flying throughout the house. But I was holding it with one arm, and it was pulling pretty hard. So I achieved something there. It wasn't spinning, So it was my way of just testing that it was actually generating the amount of thrust I expected it to, but that's probably not a very good test, to be honest. But anyway, I had throttled down, but the rotors were still spinning, and I didn't give them enough time to just coast down to zero rotational velocity, and it clipped me right here on the side of the face. And I just kept thinking, and these were carbon fiber rotors. So I'm saying here, and this item, don't use carbon fiber. You don't need it. The plastic props are just as good, and they won't cut you as much. And they act as a sacrificial part when you have a crash. So they'll break before the motors will. Carbon fiber doesn't break for anything. So it's made a pretty good cut in the side of my face. And I'm not sure plastic would have done that, but probably would have. But still, the carbon fiber was even more deadly. And you don't need it, especially time when you would need it is if you're all finished and everything is perfect and you just want to add the finishing touch. Carbon fiber will give you the extra rigidity to translate a lot of sudden thrust without flexing in the prop, so that you can move forward quickly. So I would say also, when you test, the last thing you want to do is put the props on the quadcopter. The only time, in other words, verify that everything is working, that you can change the speed of the motors. The motors are turning in the right direction. You can, if you don't have props on the motors, of course, you can kind of feel what direction they're turning. See if you go half throttle, pick up the quadcopter, move it around a little bit. Does the flight controller react by changing the thrust on the motor? Then it's alive. The sensors are connected up, so you can do a lot without having props on it. the last thing you want to do are props. So once you do attach the props, though, make sure you keep a good distance from it. Put the eye protection back on, and just throttle up a little bit, and then move the joystick to do a little bit of roll. And you should see the quadcopter just kind of pick up on one side, and then it'll roll to the other side. The other side should pick up. You don't have to fly to test basic attitude control. You can test roll and pitch just on the ground, even without actually flying. Yaw is a little bit harder, but chances are you got the roll and the pitch okay. The yaw is going to be okay too. And then very slowly power up. But power up only, so that you can just get the quadcopter about a ½ inch off the ground. And if it starts vibrating and oscillating wildly, that just means it's not properly tuned, power down. You can do all of this without actually risking the airframe in the process, or your furniture, or crashing into something in the room. So by that, in fact, all that with an off-the-shelf flight controller and one of these open source flight stacks we talked about, you can do everything you need to do just at a ½ inch off the ground before you fly. Last thing I would say is, if you have an experimental aircraft, that you don't have a lot of confidence in because it's a different shape and you don't have a lot of air time or flight time on it, you want to go through the rehearsal of the worst case scenario. And the worst case scenario is you lose control of the quadcopter, meaning that it won't respond to any of your joystick positions, and the motor is still running. You have no idea where it's going to go or the damage it could cause in the process. So you want to engineer for that in the beginning. A lot of the flight stacks have a fail-safe provision. So if they lose communication with the radio, with the joysticks, your transmitter, is the term for that. If it loses contact with the transmitter, the fail-safe will engage and the motors will turn off. That's usually one thing, and that's built into a lot of the new flight stacks these days. But there's other things you want to think about too. Is what if you go so far that you have your goggles on, you lose the video link? How are you going to come back? Because you can't. The quadcopter is this tiny little dot on the horizon. You have no idea where the orientation is. Maybe you have somebody with you that can help guide it back, but that's crazy. So you want to plan for that. The answer to that question is, you have a return to home option, and you have a switch on your transmitter that allows you to send the command to the quadcopter, because the transmitter will remain connected, and the video will lose its connection long before the transmitter does, because the range on the video is relatively short. So you flip the switch, and the quadcopter uses the GPS to come home. That's a relatively new feature on flight stacks as well also. So what I do I used to do, I don't have to do it as much now, but I was always really scared, that I'm going to lose this thing I just spent 2 or 3 months building. So I would remind myself, okay, return to home is this switch. And I would tell myself over and over again as I'm flying, return to home is this switch, return. I wouldn't actually touch it, but I would tell myself, this is the switch I need to use. This is the switch I need to use. I just repeat it over and over again while flying. Because what happens is that when you're under pressure, it's not uncommon to freeze up. And I've had many experiences doing that. And later I'll look at the telemetry of the flight to see what happened, why I wasn't able to recover the vehicle if it's a plane sometimes, why I couldn't level the flight before hitting the ground. And I'll look at the telemetry, and I actually didn't respond for maybe 3 seconds, which is an eternity if you're diving into the ground. So how is it I froze? For me, that 3 seconds was non-existent. But so the way pilots, astronauts, anybody that's going to operate under a pressure-filled environment, is you don't rely on your brain to think your way through the problem. You rely on the checklist, and you repeat the procedure in your head over and over again. If I get stuck, if it's in the wrong attitude, this is the switch. If you can make it as simple as a switch, that's ideal. So be prepared for the worst. So I don't have, let me see, I don't have any other slides, but I do have some references for you. So I highly recommend all of the stuff that we talked about. There's some great videos by somebody named Joshua Bardwell, and he's very good at teaching the basics of quadcopters. Does a much better job of explaining all that tuning that I talked about than I can. And he has a video series, it's like 10 parts, I think, where he describes the individual steps required that we went through with a soldering iron. He goes into the details. Here's how you solder. Here's where you put this wire. Here's how you mount things. Here's where here's how to do the wiring to that power control board. He goes into all of it. Somebody else, I love a classic example of a learner, somebody who's learned how to learn is Tom Stanton. His YouTube videos are very popular. He will take any project. They're not just quadcopters. He has a handheld trebuchet is one he recently did, where he can shoot with his handheld trebuchet. And there's this little arm that goes off and shoots this little ball. He goes into all the details of what he did to come up with this design. And he describes all the things he had to learn because he's learned how to learn. And he will often, which I think is the best part, he will include video of all the stuff that failed. And I think this is one of the things that makes it such a compelling thing to watch, I think, is because I'm looking at his ideas. I'm thinking, oh, it's not going to work. And then he'll try it. And sometimes it actually does work, or it really fails the way I think it's going to feel. But just to share with him, all these trials that he went through. And he does a great job of doing that in his YouTube videos. So somebody else named Justin Davis if you're interested in FPV flying, he reviews all the latest gear, and it's good to just look to see before you buy anything that's ready-made, that's designed to just fly. Tune into, check out his YouTube videos. One other person, she doesn't get very many viewers, but she's an outstanding pilot of a particular type of drone that's not very popular, but incredibly maneuverable. So we talked about, how, the drone gives you power up and the drone provides positive thrust. Well, it's possible some of the newer motors are capable of changing their direction. So they spin both clockwise and counterclockwise. If you coordinate the change in the direction of the rotors, so the flight controller is doing it in the right time, in the right way, it's possible to fly and hover upside down. And this means that you have complete attitude control, because now you can fly upside down, you can fly right side up, you can do some crazy maneuvers where you're flying sideways. And her videos show an amazing capability of flying in 3D that very few drone pilots are capable of doing. And if you want to see what's possible, that's a great video. I would say I wouldn't start with this kind of flying because it requires a lot of extra skill. So that is it for me. Do you guys have any questions about what we covered so far, or questions about engineering in general?
I guess we don't have any more questions, but
Or were you
I'll
out?
just do a little wrap up. So
Okay.
I've always been fascinated in the idea of drones. Me and my friend he has this drone. We would always record like sunsets or sunrises. We always loved the amazing artsy videos that you would get.
Yeah.
And something I actually didn't know about were these FPV goggles. It's probably like a first person view of what you can see from the drone. I always thought it was just like there's the controller and then there's a screen you would have to look at. And in addition, I didn't know about all these different types of drones. Like I didn't know there were one of them which I was pretty interested in was there's a cage around the propellers. So for safety, and drones are, in addition, drones, I didn't know that drones were I always thought they were always just for videos, photos, but then you showed that Mars drone, which you said that'll be live or presented on February 20th.
Yes, it'll the landing of the Mars Science Laboratory, MSL. Again, I apologize, I can't remember the code name for it. That's the landing date is in February. So that's when it arrives on Mars and deorbits, and then actually detaches from this arrow shell. So that's the date to watch out for in February.
Yeah, that's just amazing how a drone can be on another planet
Yeah.
carrying something, delivering something.
Yeah.
And yeah, drone, yeah, such a small object like a drone. I guess the microchipping is so important. How it like powers the different propellers, the thrusts, the pitch. It is something so small can do so much.
Yeah, I
And
agree. It's fascinating. And I would just add to one thing you say, sorry to interrupt you, but I wanted to add when you said small, one thing to keep in mind is that this approach scales. So there are people building air taxis that use the same exact principles we discussed. They might have 8 rotors instead of 4, but it's still a quadcopter. So it scales up into car size.
yeah, that's even more amazing. And
Yeah.
I think the biggest takeaway from this presentation, going away from these drones, was you saying learning how to learn.
Yes,
So
definitely.
I've never was interested. I really don't like English or history, but you saying that you were going into an English major, but then you ended up in this more mathematical, physical subject was just something that I think is really important. So I should be
Yeah.
looking out for that.
I was, I think we talked about that before the video. I was mentioning, yeah, that I started out in college in my freshman year as an English major, and I took lots of English classes. I didn't want to take any general ed because I knew what I wanted to do. And I changed along the way, and I think it was just some classes that I took that changed my direction. But I have to admit, I still, I never lost my love for for good literature, and so it never leaves you if you change course along the way. I have some friends that are engineers and also were in orchestra, and were music minors. So there are plenty of us that are able to sustain both an artistic side and an engineering side. And I think they really are what they work together. There's an awful lot of art that goes into the creative process for creating a new machine, and certainly there's an awful lot of back the other way. They think both feed into each other. Our abilities as engineers also benefit the artists as well because we're able to create new instruments of expression for them.
Yeah. So if we have nothing else to add, you guys can check out our website for the next presentation. Stay tuned for the next presentation.